So as we get started here, we have to recognize that we haven't done an awful lot of chemistry yet. This is about to change in a big way. We have talked about language, we've talked about vocabulary, we've talked about ways of saying things, how to communicate as chemists. And we're about to head into some of the underlying things that make molecules react. What makes a molecule stable, what makes it unstable? We have done some of this with the idea of induction, with the idea of resonance. Now we're about to talk about within a molecule what makes it stable, what makes it comfortable, what makes it unstable. So chapter 4, I have 125 slides here. That's a lot for a chapter. That's a big chapter. And we're going to talk about alkanes and cycloalkanes. Now, the nice thing about this chapter is they don't have any functional groups. There really isn't much chemistry in here, but there are lots of basic ideas that will follow you through all the way through terms. This idea of molecules being able to relax, or they're high energy, but they're always moving. Molecules are always fidgeting, they're always moving, and you can't freeze out that motion. So what we'll try and do today is talk about names. We'll talk about nomenclature, which I find quite dry. I leave a lot of it to you to practice. Once you get the basics down, it's not difficult. You can practice it, and we can solve problems as we go. And then Friday, we'll talk about dynamics. We'll start talking about something called a Newman depiction, something called, speaking of Ohio State, a Newman depiction, and the rotation in molecules, and the idea that molecules are not completely static. They're always moving. So we are starting now this journey which takes the rest of the 2 semesters to get through the families of organic molecules that you have to be aware of if you're an engineer, clinical laboratory science, biologist, whatever, pre-pharmacist, whatever. You have to be aware of these compounds because they show up in nature and technology and industry. So we'll take this sort of journey starting now with the alkanes, the simplest of these hydrocarbons. Hydrocarbons are simply molecules that just contain hydrogen and carbon, no oxygen, no nitrogen. And we'll work our way through the different families. We have talked a little bit about some of these things already. We know that this guy is sp3 hybridized on carbon. We know the shape of these things are approximately tetrahedral around the carbon. And we'll start relating them in the near future to their partners here, ethylene, which is a molecule that has a double bond. It's called unsaturated. You've taken a couple of hydrogens out of there and you've made this molecule unsaturated. These molecules are naturally occurring, and you can use them in all sorts of different ways to do organic synthesis, organic chemistry. So we'll deal with molecular formulae down here. We'll have to define some basic molecular formulae so we can recognize a molecule very quickly as being an alkyne, an alkene, or an alkane. And we'll build our way up through the pi bonds into the alkynes towards the end of the term. And really that's 3719. Once we get to the end of that, that's the end of 3719. Then going into 3720, we spend 2 chapters on benzene. And benzene chemistry is absolutely essential, especially in polymer chemistry, especially in medicinal chemistry. So we need to build up some ideas of what these words mean in terms of being saturated or unsaturated. Saturated means no pi bonds. You start putting pi bonds into a molecule, it becomes unsaturated. We'll deal with that later. But right now we're talking about the alkanes, which are, I guess, the simplest type of molecule. There isn't much chemistry here. They don't do much chemistry. The alkanes here are completely saturated, just containing carbon and hydrogen, and everything is sp3 hybridized. So what we need to do today is recognize that this formula fits an alkane. It does not fit an alkene. An alkene would have 2 hydrogens fewer, and so it would have a different formula. Likewise with an alkene, an alkyne, and a benzene. So the alkanes are completely full of hydrogen. Now, we need to worry about names. Most people have different names. I guess George Foreman named all of his kids George. So his house is kind of fun. George, what? The rest of us have different names to sort of designate us as being a little bit different, so you can communicate and you can understand who is who. And if you went into a pharmacy or you went into to buy some organic chemicals and you asked for this molecule in its absolute defined organic name, people would not know what you were talking about. 3S, 8S, 9S, 10R, 13R, 14S, 17R, 10, 13 dimethyl, blah, 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 would put you asleep. Right? But that's the systematic way to name a molecule called cholesterol. Now, we have seen cholesterol used as an example in my class, and we will see it in the future. That's a complicated molecule, no doubt. And if you use the rules that we're about to develop to name this thing, you could name it as you do at the bottom. Now, fortunately, because pharmacy and medicine and organic chemistry likes to keep things simple as possible, we have abbreviated names. And so the common name for this thing is cholesterol. You ask for cholesterol, you get cholesterol, because there's only one cholesterol. There's only one isomer of cholesterol that we'll see. So these names down here need to mean something. Before the exam, we won't deal with this. We'll deal with this in chapter 5 after the exam. The S and the R is the system left-handed or right-handed. That will make a big difference. But right now, we can start talking about what dimethyl means, what heptan-2-yle means, and all that sort of stuff, and start thinking about some of the basic ideas to systematically name organic compounds. Now, this is fairly straightforward. Some of you have seen this before, high school or freshman chemistry. It's much more detailed here, so keep up with it. This was developed by the International Union of Pure and Applied Chemistry, IUPAC. You can see the website here. absolute rules that will define any organic molecule. And as the molecules get more complicated, you can see how powerful this is and how useful it is, because you can give a very complicated system a definitive name that does not match anything else. You definitely get the right molecule if you ask for it. We'll talk about the basics today. We'll talk about the simple things, about how to put chains together, how to put cycles together, and how to put substituents on those molecules so you can give a confident name. So if you look at this, this is not as complicated as cholesterol, but I think it's still quite difficult. We've got some prefixes that we'll have to worry about in terms of the numbers. What do they mean? That will tell you about the geography of the molecule, where groups are on a system. And we've got now the use of YL at the end. Instead of hexane, this will be hexyl. Hexane is a different molecule to hexyl. Hexyl is a fragment on a bigger molecule. And we'll have to be able to come up with molecules like this. Now, you're not going to see this on the exam next week. Maybe on the final, where you have to come up with a name as complicated as that, but we'll work our way towards that. So next week, we'll have to name some fairly simple systems using some basic rules. So to get started, if you've been reading ahead, you know that this isn't difficult. You just have to keep up with it, and you have to practice. That's the most important thing here. The IUPAC rules for naming alkanes. This is the basis for all the other nomenclature. Once we get alkanes out of the way, we can do alkyl halides, alcohols, all those other things, but this is the basic stuff. We can see now that what we have to do when we're given a molecule is to look for its longest continuous carbon chain. That's going to be fairly simple, but most of us read left to right, and the temptation is at the beginning that you just go from left to right, and you try to find the longest chain left to right. That's not necessarily going to work, because organic molecules are not static, and we've got to be able to look at them from right to left, upside down, all other directions to follow the rules and to make sure we're happy with this. We have to identify substituent groups. Basically, that's anything else that is not part of that longest chain. Once you define that longest chain, everything else becomes a substituent, and I'll show you tricks to be able to do this. We number the chain to keep the numbers small. What that means is your substituents would rather be at 1, 2, 3 rather than 7, 8, 9. Just keep the numbers as small as you can, follow some sensible rules, and this isn't difficult. And what we come up with is this idea of the name should comprise of a numerical location. In other words, at the front, you have some numbers that tell the person reading where those substituents are on that chain. And then you have the substituents themselves. Sometimes they're in parentheses if we have to make a more complicated substituent, which needs some branching involved. And then we would put the name of the parent alkane. The parent alkane is obviously the family name. It's related to other molecules, maybe with different numbers, different substituents, but there's the basic idea. So for a very simple example, 2,3-dimethylheptane. Again, I'm going to ask you to memorize some pieces of information, some prefixes, so you can know what some of the alkene prefixes are. And after you've done that, you know them for all the other systems we have to worry about. So the 2,3 here is telling you numerical location. The dimethyl here is telling you something about the fact that you have some methyl groups attached. They're the substituents. And the heptane at the end is the parent alkane. Nothing tricky to this stuff. So get started. The book is very nice about this. The book is well put together in terms of a pictorial sense. You can actually read this quite easily and get these ideas. You choose the longest chain. You try and find the longest chain. And in this particular example, it happens to be 9. So if you're in the habit of reading left to right and you start 1, 2, 3, 4, 5, 6, it doesn't work because you're not following the rule. You've got to find the longest chain within this system, looking from any direction. Top to bottom, left to right, doesn't matter. Find that longest chain. And in this case, we'll find that the longest chain has 9 carbons. The way I was taught to do this, which I think works quite nicely, is you write it down. You make a shopping list. You write a list of things as you go. So I've got 9 carbons. I have to worry about what the prefix is for this, but I've designated the parent. What we have to worry about after that is what are these things attached, because we haven't dealt with these things. These are going to be the substituents, and we're going to have to tell the person reading where those substituents are. So the longest chain now needs a name, and I'm going to ask you to learn up to 12. It's not as arduous as it sounds, because most of it is logical after you get to 5. The prefix for 1 is meth. It's not methane. A methyl group, when we see it, is a CH3 group. Methane is CH4. So we have 1 hydrogen taking off, and we can use that extra valence to bond to something else. So this becomes a substituent on something else. So meth is number 1, eth number 2, prop number 3, bute number 4, and then it gets logical. Pent 5, hex 6, hep 7, etc. Once you get down to here, dec should be obvious by now for 10 using the decimal system. And then the ones I stop at 12. Know through C12 and you'll be happy. Okay? It's not often we see in this class molecules that have bigger chains or longer chains than that, so we'll stop at 12. I always remembered 11 under. 11 is under 12, so undecane is 11 and dodecane is 12. Those are the prefixes you must know by now to be able to communicate organic structures from now on. With those in hand, we can start talking about how to put these things together. Now, there's a general idea that you want to keep things as simple as possible. This slide is trying to show you that you have several choices of how to put these systems together, and there's one that is more correct than the other. You can get away with both, but one is more correct than the other. And again, if you're going to be taking an MCAT, a PCAT, or a DAT, or any sort of standardized test in the future, you want to know the best way to do these things. So the correct way to do this is to have your substituents have as many as possible. What that leads to is lack of branching. If you try to minimize the number of substituents, you end up with branching within the branch. And you can imagine how complicated that would get. You have a long chain which has things sticking off of it. Those branches become branches become branches. That's going to be more complicated than necessary. But if you go to this idea of keeping the substituents, 3 instead of 2, you get some very simple substituents. This will be a methyl, this will be an ethyl, this will be an ethyl. That's much easier to come up with and much easier to write down than if you have multiple difficult branch substituents. So just keep this simple. The parent here is 7 carbons. Again, you just have to do that with a pencil or a pen, trace through, and you'll find that 7 carbons is correct there. And then we have a choice of having 2 substituents or 3. I'm saying that 3 is better because they will end up having more simple names than if you had 2 substituents. So there's a process here. We've named the precursor. If you think about 7, what is the precursor for 7? Heptane. So going on, we need to start thinking about different types of systems. I'm going to point you towards my website. There are many different things on there to help you with this stuff, practice, tutorial type stuff, and then we'll start to put this all together. By the end of today, I'll get into cycloalkanes. I'm not so concerned about that just yet, but we'll carry on with the straight chain molecules, and then we'll hopefully finish today with cycloalkanes. Now, we have a molecule here which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what's the precursor? Decane, right? So I was taught to write down a little shopping list. I think my molecule is related to decane. It isn't decane itself, because decane wouldn't have any branches sticking off of it. But as a derivative of decane, that would be the end of my name. And then I've got to worry about the names of the substituents, and it's fairly simple. If you know the precursors for the other groups, then you know the precursors for the substituents. This has 1 carbon, right? 1 carbon is methyl. And this slide I'm going to point out the ending. It's very easy to get this wrong, and those who like the big red slacker pen, it's very easy to get this wrong because you're not keeping up. You've got to recognize that YL is telling you something. If you write down 4-methane decane, it doesn't work, because methane is a different molecule. Methane is CH4. This is not a CH4 group, it's a methyl group. So that's telling you that it's a substituent on something else. So now this ending is something that maybe we haven't seen so much of, but it's really important. Well, what's going on out there? Calm down. I have 2 carbons over here. You'll recognize that as eth from our chart. And I've got 3 carbons here. That's prop from our chart. And that's going to be fairly straightforward. So the job here is to wake up and to listen to what I'm saying so that we don't get this wrong next week. Now, there are some things here that aren't quite satisfying. They aren't quite completely, I like this stuff, right? And it's an attempt, again, to keep things as simple as possible. You're going to find complicated molecules. You'll have a choice of how to put them together with the names. Sometimes you will be allowed to call this a substituent and this the parent. And in other examples, when it happens to be more convenient, you might call this the parent and this the substituent. And we'll develop 2 types of names, substitutive later on and functional group later on. But right now, we're going to try and keep things simple. Now, the parent here is the cyclohexane. Okay, cyclo, because there are 6 carbons, cyclo because it's a cycle, hex because there are 6 carbons, ane because it's an alkane. So we have a cycle now with 6 pieces attached. But then we have a group here. How many carbons in that group? 3. What's the prefix for that? Prop, right? So we'll call it propyl cyclohexane. We get through some of this fairly straightforwardly. Later on, this group here, which is a cycle, it might be more convenient to call it a substituent. And you'll find now, maybe not as simple as this, but if you have something over here which is just horrendously big and branched and ugly, and it's just easier to call that a substituent on the bigger piece. How do you get this? How do you work this out? You practice. You see how it's used, you see how it's applied, and it sinks in, I think. So here again, we recognize a 3-carbon piece, happens to be a cycle, so the cyclo prefix goes in. And in this example, bute, where does bute come from? 1, 2, 3, 4, that's the longest chain, and we're giving it a number. Why do we need numbers in these things? to tell the reader where it is, because if I put that cyclopropyl group someplace else, say here, it's not on the 1 carbon, it's on the 2 carbon. So we have a difference now. Ashley. No, that's a very good question, actually. Let's go back and look at that. Why isn't there a number on this one? Do I need a number? If I put my propyl group here, is it a different molecule? No, it's still 1 propyl cyclohexane. You don't need it because it didn't change. On the next slide, if you put your cyclopropyl group here, it becomes 2 cyclopropyl. It's at a different point on the molecule. That's a little difference that you'll see with cycles, and this is why we want to get into this now, so that we're not lost next week. Is everybody okay, Mr. Benedetto? No? We're going to find out. So there is a process here. There is a method to be able to do these things. It's fairly straightforward. Look at the molecule. It doesn't matter how big and ugly it is. In this class, C12 is the maximum longest chain that you'll see. So we'll find out that longest chain. And then what we need to do is recognize that we have dealt with each of these carbons. We have looked at those carbons, right? So maybe I put a little pencil cloud around them. I don't need to worry about that anymore because I'm done with it. What I haven't dealt with is this, which happens to be 1 carbon, so methyl. This, 2 carbon, so ethyl. Over here, propyl. And then down at the bottom, we also have that one there, methyl. And do that as you practice. Do that as you start. It's a very simple way to keep a track of things so you don't get lost. And then make your shopping list and put it all together at the end. Now, I'm a big fan of partial credit. So if you do one of these things and you get it mostly right, you get most of the points. If you don't do it, you don't get any points. I can't grade blank space. Okay? So if you make an attempt and it's reasonable, you get points. You get it right, you get all the points. That's how it works. So we can start thinking now about how to put this name together. And it turns out, if you think about how that's going to be done, again, it's sensible. It's simple. Keep the numbers simple, keep the numbers small. That will mean maybe numbering from one end instead of the other, so the numbers are smaller. And also then alphabetize. Even though methyl is a smaller group than ethyl, the ethyl goes first for a very simple reason. E comes before N. Alphabetize things. So I've got a couple of things going on here. E for ethyl goes first. What does the di mean? What does di mean? 2. There are multiple substituents. 2, 3, 4, di, tri, tetra. Fairly obvious. And it turns out now that that D does not count in the nomenclature. You don't count the D's. You don't count the T's for tri. You're looking for the name of the radical, the name of the substituent. In this case, it's methyl. So E comes before M, and M comes before P. So that's why you have it numbered there. It's not because of how important things are. It's not because of one group is bigger than the other. It's simply keeping it simple by alphabetizing it. That's all there is to it. Okay, so moving along. I'm going to fly through this stuff unless you stop me. I think this is fairly straightforward. Many of you have seen it before. There's much more interesting stuff to come to get into. So in this example, we've got to worry about the fact that that's a branch. What am I calling a branch? That's a branch, right? You have a tree with trunks. That's a branch. I'm not very good at drawing, but take my word for it. And then from branches, you can have branches. Yes? And from those branches, it can get complicated and you can have more branches. That's all we do here, is talk about the branches. So my parent is the tree, and my branch is the branch. After that, I have to worry about how the branch is attached. If it's attached on the first carbon of this propyl chain, that's one possible organization for that molecule. And I would call that propyl. But I could now take this radical, this piece, and attach it at this carbon. And that's the difference here. It's attached at carbon 2. That's a different piece. It's a different shape, therefore it's a different molecule. So this straight chain branch here is the simple parent, propyl. And this one over here is an isomer of that. It's simply a different pattern, a different way of adding the pieces together. So, common sense, let's call it isopropyl. So every time you see this tail, like a fish tail, that's an isopropyl group. 3 carbons pointing like that, that's an isopropyl group. What you'll have to get used to for pharmacy, for medicine, stuff like that, for CLS and laboratory science, is the use of both. The trivial old names, which is often quite easy, and the systematic names, which are helpful if you don't know the trivial name. So here I've got something different now. Here I've got something called a 1-methyl ethyl. Where on earth did that come from? Well, I'm going to set up a set of rules again, the same set of rules. I have a branch point. I'm defining my branch point. If I completely forget that this is an isopropyl group, I can still name it systematically. There's my branch point. That's carbon 1. What's the longest chain coming away from that carbon on that piece? 2. That's where the ethyl group comes from. 1, 2, right? This is what type of group? It's a CH3, so what should we call it? Methyl. Where is it on my chain? Carbon 1 or carbon 2? Carbon 1, 1-methyl ethyl. That's where that comes from. We'll practice them. You'll see many more of them. And you will be experts at this stuff. What's your name? Haley. Probably is. Go on. Yes. Depends who you're talking to. No. No, that would be redundant. That would be the same, saying the same thing twice. Sarah. Because that's not following the rules. The ethyl is the longest chain, right? And we didn't alphabetize the longest chain in the previous examples. That's the parent. That's the longest chain. Jordan. You can use colored pencils. You can use whatever you want to. Pens, except red, because red's my favorite color, and we're not using that. Yeah, as long as I can read it, yes. As you get to the third exam with the mechanisms, people bring colored pencils, they draw dragons, Harry Potter. They draw all sorts of other things to avoid doing the chemistry. But, you know, that's fun. Ashley. Yes, but it'd be the same thing, because if I turn that thing over, it's identical. Practice this stuff. It's not easy, but it isn't difficult. So we need to worry about some other things. You think about some of the pharmaceuticals out there. Ibuprofen. What does ibu mean? It means isobutyl, right? These things are derivatized. These things are compacted into pharmaceutical names. Many of you are interested in that field, so we should be aware of these things. And when I have 4 carbons now, it's going to get more complicated because I've got more possibilities for how to put those carbons together within the chain. So we've got something over here. It doesn't matter what this is, right? That parent is something else. And we've got a butyl chain. 1, 2, 3, 4. You learn the prefix, that's it. It's a butyl chain. So now I have the possibility of different ways of adding these things together. I can shout all day to keep you awake. We have a sec-butyl. This is sec. You can think of it being on the second carbon, if you like. That's on the second carbon, so let's call it sec-butyl. And notice now the prefix is italicized, right? That's telling you it's not really part of the molecule, it's just a little device to show you what the shape is. Now, my 1-methyl propyl should be fairly obvious. What's the longest chain away from that carbon right there? 3. 1, 2, 3. Yes? And what piece is this? Methyl, and where is it? Carbon 1, 1-methyl propyl. They are the same thing. Sec-butyl is the same thing as 1-methyl propyl. Now, because you have more pieces, you have the possibility of putting these things together in different ways to get different outcomes. So again, my parent doesn't matter. Here, I've got isobutyl. It's an isomer of the others. Let's call it isobutyl. It also looks a little bit like the isopropyl that we just saw. That's the way I remember it. It has the fishtail. Therefore, it belongs to the iso group. It's an isobutyl. Why not propyl? It has 4 carbons instead of 3. So therefore, isobutyl. This nomenclature down here becomes fairly apparent fairly quickly. There's 1, there's 2, there's 3. That's a propyl chain. And this now is a methyl group at carbon 2 of that chain. That's why that becomes 2-methyl propyl. Go ahead. No, you're numbering away from where it's attached to the parent. That's the rule. You number from where it's attached to the parent in that chain. On the right-hand side, something you'll get used to a lot, the little chicken foot thing. This is tert-butyl. Tert because it's a tertiary carbon. We haven't defined that yet, but it has 3 carbons attached to the center, so we call it tertiary. This is tert-butyl. Again, this prefix is italicized. And we'll find now that this can be abbreviated. Anywhere you go here, it's really 1 and 2, so that's the ethyl group. And then I have a couple of methyl groups, that's why I have dimethyl, and they're both at carbon 1, so I call it 1,1-dimethyl ethyl. That's a T-butyl group. Brienne. This is a fine question. This is a fine question which is about to get really annoying. Not because you asked it, because it's an annoying situation. I'll answer that by doing this. This is how much detail you need, Mr. Benedetto. I'm sure Ms. Herchek is really fascinated in what you have to say, but, you know, she wants to learn as well. In these molecules, I do not alphabetize that. If it's italicized and hyphenated, you don't count it. If it isn't, and it's all part of the same name, you do. Not my problem. I didn't invent this. But that's the level of detail you need to have to even pass my class. Never mind do well in my class. So I have here the sec doesn't count. Isobutyl does. The I counts. And for isopropyl, the I counts. Right? But over here for tert-butyl, the T doesn't count. Blame the French. I do. They came up with it. So you've got to be on top of this stuff or else it's not going to be much fun. So we're going to start thinking about bigger systems because most of you have to go into bigger subjects, biology, engineering, stuff like that. Pentyl. Pentyl, obvious because I have 5 carbons and I can see now there will be more different ways of putting these things together. I've got the straightforward pentyl one and here I've got isopentyl. I remember it because it looks a little bit like isopropyl. Once I know isopropyl, I can count to 5 carbons and therefore isopentyl. Down here, 3-methylbutyl. 1, 2, 3, 4, there's the butyl. That's carbon 3 of that chain, and that's where the methyl group goes. So 3-methylbutyl. Now, the other one over here, neopentyl. There are more, but these are showing you some of the more complicated ones. I have neopentyl, right? So neo, new, different. There are 4 carbons, there's the 5th one, that's where the pentyl comes from. It looks like T-butyl, but now the N counts. So again, for the future, know these things, not just for my class, and that name should become fairly obvious by now. It's systematic and it works, as long as you know the rules. You need to know those rules. Go ahead, John. What if it was, so you'd end up, there are others, like I said, there's your parent, and you could have something like this, right? There's 5 carbons, which is not shown on this slide. That's a different isomer, isn't it? Yeah, so that's 2-pentyl. Isopentyl has to have this arrangement where this is the first carbon, and then you have the other 4 carbons sticking off like that. It's the only way you can do it. If you move it around, reattach it someplace else, it's not isopentyl anymore. Now, for homework, draw them all. They're not all on there, but have a go at drawing all those substituents and having a go at the names. Ashley. Yes, but it's not a butyl. That tert-butyl is only when it's got 4 carbons. This is now a little bit different. I'm over here. He's over there. I wasn't late. Now, let's talk about this systematically. Let's talk about this in terms of sensible things to do. So you pick it up now and you know it for the future and you can take it with you. So in this example, we need to put things together in a sensible way. I have got a carbon system which has 6 carbons in it, 5 of which seem to be in a longest chain, and then I've got my thing left over. Circle it with a pencil. It's got 1 carbon in it. It should be a methyl. 2-methylpentane. Easy enough? Nothing tricky there. But if you move this across to here, that becomes 3-methylpentane. That's an isomer. That's not the same molecule. It'll have different properties. It'll have a different name, different boiling point, whatever. It's not the same molecule. So again, in this example, why not label from here? Why not start the counting from over there? Because I'd end up with 4 instead of 2. I want to keep it simple, so I'm going to keep it down at 2. In this example, same sort of idea. Yes, we learn to read left to right, but organic molecules don't understand that. You have to just name it correctly. This is wrong not because I'm coming from right to left, but because my number is bigger than it needs to be. It's as simple as that. As we start to get more complicated, you're going to have to make decisions about the second number and maybe the third number in these systems. So in this example, I've got methyl groups. If I look at my longest chain, it looks like that, which is 7 carbons, right? So what's the name for that? Peptane. And then I've got methyl groups here, here, and here. I've got 3 of them. So what prefix should I use for 3? Tri, T-R-I. And they are methyls, so trimethyl. And then I have to tell the reader where they are. I could say 2,5,5, or I could say 3, 3, 6. There's 2 wins. Look at the first number, keep it as small as you can, that typically wins. Logical. In this example, we have to go further because both ways of doing this, from left or right, give you a 2 as the first number. Then you have to move to the second number. That's fairly obvious. After that, it turns out that this one, reading from right to left in this example, gives you a 3 as opposed to a 5. This one wins. There's nothing tricky about this if you are keeping up with it and being sensible about it. Now, in terms of cycles, they become a bit more complicated once we start putting other groups on them, but for alkyl groups, it's not too tricky. In this example, I could number from here as my carbon 1, or from here. I don't number from there because there's no substituent. That just seems silly. I focus on the substituents. So I can go from right to left or left to right. If I go here, I'm going to end up with 2 methyl groups on carbon 1 and 1 on carbon 3. But in this example, I end up with 2 on 3, so it's obvious that that beats that. Well, straightforward points. So here's the rule, or here's the idea. Find the longest chain within your system. Use whatever device, colored pencils, chalk, whatever you want, to work out that the longest chain. Now, does the longest chain also go from there? Yes, it does. Because these 2 alkyl groups are the same, it doesn't matter. As long as you get the same longest chain, you're fine. Then you label them with what else is left. We have methyl, ethyl, methyl here. And then you write down your list with some numbers to keep them as small as you can, and then you put it all together. So in this case, 4-ethyl, 2,3-dimethyl octane. So again, just to reiterate, I alphabetize the substituents. I do not count the D or the T in tri or di. That's just a rule. I said to keep it simple, keep it sensible. So examples, very straightforward. What's that called? How many carbons? What's the prefix? Hex, hexane. Do I need any numbers? No, no substituents, hexane. What about this? 2-methylhexane. There's 1, 2, 3, 4, 5, 6. That looks like a methyl group at 2. Let's call it 2-methylhexane. Okay, you can see what's coming up on the homework and the quiz for chapter 4, part of it. I've got a couple of substituents here. What's my longest chain? So what's the prefix for that? Heptane. Where are my methyl groups? 2 and 4. So what is it? 2,4-dimethylheptane. They're the straightforward ones. It obviously gets more complicated as we get through this stuff. Now, this one looks a bit ugly, but it's on the way to where we need to be. Longest chain, 1, 2, 3, 4, 5, 6, 7, 8. So what's the prefix? Octane. I didn't talk about this. What is this? That's a methyl. What is this? That's a methyl. What is that? Ethyl, right? So I've got to put an ethyl group somewhere. I've got to put a couple of methyls as a dimethyl. How about some numbers? Four ethyl, 3,6-dimethyl octane. Practice them, do well at them. There's no such thing as a giveaway point on these exams, but this is going to be as close as it gets. And this exam needs to be done well because the rest of them are more difficult. So, cycles, that's a bit more tricky. Am I going to call this one or am I going to call this one? I'm going to call the top number 1, right, because then I can put 2 methyl groups at 1. How about 1,1,3-trimethylcyclohexane? Good enough? Okay. What about that one? Now, you've got to get used to this stuff, and this is the amount of detail you need to get in this stuff so you don't take my class twice, 3, 4 times. What is that? That's a tert-butyl. It certainly is. Joe shoots and scores, right? That is this guy, but you don't have time to do all that stuff, do you? Because you're busy doing everything else. You've just got to recognize it. That's a T-butyl group. So T-butyl cyclo what? Heptane. Don't forget the cyclo. People forget the cyclos. You could also call it 1,1-dimethyl-ethyl cycloheptane if you want to. Tert-butyl is the abbreviation. Down at the bottom, cyclo what? Pentane. What are these groups? Methyls. What is this? Ethyl, right? So what am I going to call number 1? Top or the left? I think the top, so we keep it simple, right? 2-ethyl, 1,1-dimethyl cyclopentane. So be very careful here. The numbers don't necessarily have to go in order. The alphabetization does, and then the numbers match those alphabetizations. Mr. Metz? I think it's because I had to take it onto the next line. But you wouldn't put that hyphen in there. Okay. Now, there is a sort of, there's perfect, and there's fairly close and okay. Fairly close and okay gets you a C, perfect gets you an A. That's how this stuff works. Oh boy, that's painful. Okay, but you all have to be able to do that by next week. Cyclooctane, you've got an isopropyl, isobutyl, a couple of methyl groups, put it together like that. And again, this is hyphenated, you need to know that. You don't include the S, you include the B. And this is not hyphenated, so you do include the I, and the rest of it falls into place. Some fairly simple rules you can get a hold of to do these things, do these problems. Brienne, okay? All right, good. So, bicycles. You'll grow to love or hate these things. I love them. Jordan. Oh, we're not talking about any ols yet at all. Possibly. Possibly, yes. It would have a different name if you change things around, absolutely. But we haven't put any functional groups on here yet at all. You're not going to see anything like that yet. So, one of the challenges you will have in my class is drawing these things. And we'll practice them in recitation. Drawing bicycles. They are all over the place in pharmaceutical chemistry, to be able to put these things together. They aren't alkanes. They do fit the alkane idea. And they're tricky, because they now seem to have two cycles that share at least two atoms. Right? So the bicycle is because of that. And the problem is you have to name them, you have to be able to draw them. And you have to be able to do it in both directions. I can ask you to draw it from the name, and also ask you what the name is from a picture. So butane, cyclobutane. Cyclobutane is because you have 4 carbons total. But that's not cyclobutane, that is cyclobutane. If you put those two atoms together in the middle, you get bicyclobutane. That's the difference. Now, why no numbers? Because there aren't any other isomers of that molecule. You can't put those 4 carbons together any other way to get a bicyclo compound. If that's the case, you're done. It's one name, no numbers. But if you move up to bigger systems, you're going to have the possibility for putting together the atoms in different ways to get different compounds. So we have to be okay with this, and there is a process, there is a rule. This molecule down here is said to be bicyclo 3,2,0 heptane. Where do the numbers come from? Well, it's fairly simple if you're awake and you follow the rules. I'm going to label with a couple of dots my junction points, where the cycles meet. Because from there, I'm going to count away. First of all, I'm going to count the total number of carbons to make sure it says heptane. I can see 5 from that side, and I can see 2 more over here. That to me is 7. So I have 7 carbons. That gives me my cycloheptane. It doesn't tell me just yet what the numbers mean. So we have a device. Simply, what you're going to do, Ms. Jadu, this is what you're going to do, is count away from those pieces, from there to there to there. How many carbons is that, biologists? That's 3. It always is. That's where my 3 comes from. Going in the other direction, from my junction point, I do not count my junction points. I have 1 carbon over here, I have another carbon over here. How many is that? That is 2. Now, where does the 0 come from? Because going through in the other direction here, there are no extra carbons. 3, 2, 0. I can put those atoms together in a different way. On the right-hand side of the slide here, I have them in a different way, a different order. And that gives me a different molecule which you have to be able to differentiate. So looking at this, the bicyclo became because you have 2 cycles joined together. The 3,2,0 is based on a fairly simple device that you should learn. And then the heptane is just the total number of carbons. Ashley? Because you can't put those atoms together any other way to make a different bicyclobutane. You don't have enough atoms. So let's go over to this side now. Let's deal with this one. How many carbons total in that system? 7. That's where the heptane comes from. It's bicyclo because it has the same sort of idea where 2 cycles are joined together. Why can't I call it 3,2,0 heptane? Because they're not arranged in that pattern. They're arranged in a different pattern. So I'm starting, I keep my numbers going from top to bottom. I go from large to small. These details count. In this direction, how many carbons do I go through to get back to the junction point? 4. That's where my 4 comes from. In this direction, how many? 1. In this direction, from top to bottom, none. You will need that third number in a minute because you can go in different directions and get different numbers. Joe?
These numbers,
Yes. Start large and small. So I'm going back up to the top one. I'm going to this. How many carbons total? 5. You've got 5 carbons. That's a pentane. Bicyclo because we have the 2 things joined together. I can think now about putting some numbers in. I do need some different numbers now because I can rearrange this to make different molecules. And in this example, I can see, for example, the 2 comes from going in that direction, the 1 comes in that direction, and the 0 comes from through there. It's a fairly simple device that you need to be conversant with. The more complicated ones are at the bottom. When we ask you very quickly in the near future to draw these things from scratch, and you have to have a go at them. You're going to see products like this, you're going to have to draw them. So how many total carbons in that molecule? 8. 1, 2, 3, 4, 5, 6, and a bridge going across. And that bridge going across is why you need that third digit, because there are carbons in there and you have to count them. Octane is fairly obvious. The bicycle is fairly obvious now. 2, 2, 2. Going from the junction carbons, which you should probably label to start off with. If I go in this direction from here, around here, to get back to the other junction, how many carbons do I go through? 2. What about in this direction? 2. How about over there? 2. If I had 3? 3. But I don't have 2, so it's 2. Look at this one over here. Now we're heading to things like tropanes, heading to things like cocaine and lidocaine and stuff like that, drugs. You can see here, bicycloid, because it's got a couple of cycles joined together. Decane, there are 10 carbons. You've got to be able to draw these things from the name next week, not just the other way around. You've got to do both directions. In this molecule, I start high, so I'm going to go here. There's my junction. There's my junction. I'm going from here, 2, 3, 4 to get to there. That's where my 4 comes from. 2 in this direction, 2 in that direction. That's where my number comes from. Nothing difficult unless you ignore it. Then it's impossible. Okay? Next week is going to be fun. It's going to be the build. It's like, oh boy, something you've never seen before. Now, I am flying through my slides. I thought I would get through about 30 slides today. I got through 47. That means I'll get most of chapter 4 done by next week. But that's what you want, right? You want to succeed. That's fine. Now, this chart is something that gives you an idea of why the subject can be so intimidating, but also how you can handle it. You can think about this as, why does the organic world get so big so quickly? And the answer is fairly simple. If you have CH4, there's only one way you can put together those atoms to make an organic molecule, and it happens to be CH4 that we've dealt with when we did hybridization patterns. So there is one isomer of that. If you start to put together 2 carbons, you get CH3, CH3. That's it. You can't do anything else. That's ethane, one isomer. You put together 3 carbons, that's all you've got. You put together 4 carbons, all of a sudden, straight chain and a branch. I can make different isomers. Now, as you work your way through here, it starts to get more complicated. And we get 3 isomers, we get 5 isomers, 9 isomers. Okay? Once you get to 10 carbons, you've got 75 isomers. You don't need to know all of them. You just have to have a way or an idea of how to put them together. It's systematic. Longest chain, take off an atom, put it somewhere else, move that atom around, make the 2 isomer, the 3 isomer, the 4 isomer. That's hopefully what you've been practicing in the book. Now, 40 carbons. Let me put this into context, in perspective. 40 carbons is a small molecule. That's a cholesterol type molecule. Biological molecules, proteins, you're looking at thousands of atoms. And thousands of atoms, carbohydrates, stuff like that. If you have 40 carbons, and you want to make alkanes just from those 40 carbons, no double bonds, no functional groups, nothing else, you get 62 gazillion, 492 bazillion, 109, you get a lot. I don't even know what those numbers are, but that's a lot, okay? Just by being able to put these pieces together in different ways. That's why the subject is so big, and I guess inexhaustible in terms of the number of molecules you can make. But we're trying to learn this systematically so we can handle this stuff. You need to be able to do things like this. You know, if you can do C6 or C7 with those 5 or 9 isomers, you're fine. But you should recognize now that alkanes, which are the simplest building blocks that we have to deal with here, are very, very diverse, simply by changing the atoms around in a very simple sense. Okay, so what we've learned today is that alkanes are important. They are the building blocks for what we need to do. And I'll leave you with this idea. We've got a couple of minutes left yet. You're going to be asked a question like this, whether it be now or on the next few exams, at some point, to make sure that you're able to do this. You can conquer this. I have 1, 2, 3, 4, 5, 6 carbons. That's hexane. To a chemist, I have 6 pieces of Lego. Right? I have 6 Lego bricks. And I can put them together any different ways, many different ways. And I can think about this now. I'm trying to exhaust the possible number of isomers from my chart I just I showed you. Apparently, 6 carbons has a certain number of isomers. Where do they come from? Well, I have the straight chain isomer every time. What you will learn in this chapter is that that is not a different molecule. That is simply a bond rotation from the molecule above it. They are the same molecule. That's a big deal in chapter 4, certainly before the weekend, is bond rotations. Now, I still have 1, 2, 3, 4, 5, 6. I have 6 above. They are the same molecule. They are not different isomers. Be very careful as you practice these things in chapter 4. Systematically, the way I was taught to do it, if you're asked to draw all the isomers for a molecule, draw the biggest one first, draw the longest chain first. Then go down to the next number of atoms. I started with 6, I'm going to go to 5. And then put back on the other piece, the other Lego brick. That's a different molecule because it has a different way, different connectivity, if you like. And I have to worry about isomers. This is my 2 isomer. If I move my methyl group across the chain, that's the 3 isomer. If you understand the nomenclature, you can get the answers right here because you just apply that nomenclature. 2 and 3 are different molecules. So this would be 3-methylpentane. That is not the same as this. This is 2-methylpentane. Go to here. I think I've exhausted that. If I put my methyl group there now, I get back to this guy, simply by turning it over. That's a big deal now in this next couple of days, is recognizing that you can look at molecules from different directions, but it's still the same molecule. Go ahead. Yes. Same name, same boiling point, same postcode, whatever you want. Yes, they're the same thing. Well, I've exhausted my 5s, so I'm going to go to a 4-carbon chain, and now I have 2 pieces to put back on. I could put them back on the same carbon and make 2,2-dimethylbutane, or I could put them back on adjacent carbons and make 2,3-dimethylbutane. And I carry on until I've exhausted all my possibilities, and that's not as easy as it sounds. That's quite tricky. And what will make a lot of you fall down because you're not keeping up to the level required is drawing stuff like that and going, that's different to that. And they're not. They are the same molecule. And you have a little test. How do you know they're the same molecule? Name them. If they have the same name, they are the same molecule. That's how you check. So I'm going to carry on Friday, and I will be into, give me a heads up, I will be very quickly into this stuff. If you have molecular models that you bought, bring them with you on Friday. Hang on.
The last.
Hang on.